Okay. So, welcome to this extra and last problem solving session for course Circuit Complexity Theory. So, the deadline for week 12 assignment was yesterday. So, today we'll solve the 12th assignment and then we'll recap whatever we saw in the entire course. Okay. So, let's start. The problem is a Boolean function on n variables is called non-degenerated if it depends on all of its variables. Formally, the output is different for xi equals to 0 and xi equals to 1 for all I. Show that any circuit of an into computing a non-degenerate function f must have size at least n minus 1. So, uh, ex- before we start, let's look at an example of a non-degenerate. What's wrong with my video? Okay, seems fine. Okay. So before we look at the problem, let's look at some examples of non-degenerate function. So for example, OR is a non-degenerate function, AND is a non-degenerate function, XOR is a non-degenerate function because let's pick OR. So and pick any I, right? Then the OR of this all zero string is zero, and the OR of the string, which is all zeros except at location I where it is one, right? So OR for every I, there exists two strings, x and y, such that OR of x is 0, OR of y is 1, and x and y only differ at the ith input. Same for and for XOR. Okay. So now that we looked at some examples, let's prove this. So yeah, let since C is uh, circuit of an into. Okay. So the first claim is the following. So first, we'll show that for every I in N, C must have a leaf labeled by Xi, or in other words, it must read Xi. Now, intuitively, this makes sense, right? Because if it misses any variable, then there exist two strings which only differ at that variable, so that their values are different, right? So the function values are different. So if it misses that variable, then for both of the strings, it would output the same function value, which is a issue, right? So by contradiction, Uh, yeah, so now if, okay, I should rather write EM because I'm using experiment. Yeah, yeah. So since C does not even read xi, it does not depend. Its output does not depend on the value of xi, right? So the output of C is the same as the output of a function g, which is on n minus one variables with xi missing, right? So yeah, then C of A is equal to g of A1 to A I minus 1 an, but A1 to AI minus 1 and AI plus 1 to AI are the same as B1 to BI minus 1, BI plus 1 to BN, right? And this is just CB. However, yeah, this contradiction proves our claim, right? So now we know that our circuit C must have n loops. Okay, uh, at least n loops. Since C is a Boolean circuit, if n in 2, size S, the gates in all the gate. Yes, so C has S gates, and it's a fan into circuit. And so the number of children of the gates can be at most 2s, right? At most, because some of the gates might be not gates, they might have just one child, right? However, except the root, or except the output gate, I should say, each of the gates is a child of some other gate, right? And so we are left with at most 2s minus s minus 1 is equal to s plus 1 children that can be used, right? Yeah. Okay. Why is my tab completed? Okay. Yeah. Now the screen can active. Okay. So we have at most s plus 1 children that can be leaves. And since there are at least n leaves, this means that yeah, this is what we wanted, right? We wanted the size to be greater than n minus 1. Yeah, that we have shown. So a slight generalization of this. So suppose that instead of C being a circuit with fan in 2, let's say it were a circuit with fan in K. Okay. Then what can we say over here? So what can we say about the size of C in that case? Okay. So let's quickly look at this. So this claim remains as it is. This is true regardless of the sign of the circuit, right? So now, since in that case, since C would be a circuit of fan in K and size S, the number of children of gates in C is at most K times S, right? However, again, except the output gates, each gate must be a child of some other gate. So we have at most Ks minus S minus 1 gates, and that is K minus 1 times S plus 1 gates, right? So if we would have at most, and n less than or equals to sorry, n minus 1. Oh, wait, no, this is determinant, yeah, implies S is at least n minus 1 over k minus. So this is the generalization, and if you put k equals 2, you recover this. So is this fine? Or give me a sec. Okay, yeah. So now let's quickly recap what we saw in the entire course. Yeah, so okay, so in the course we saw a lot of lower bounds for different models of circuits like formulas, monotone circuits, constant depth circuits, etc. Right? And the first thing, and most of these lower bounds that we saw were explicit, right? So the goal of circuit complexity is to prove explicit lower bounds against different circuit classes. And by explicit, I mean that the function family for which you prove lower bound must have a nice description. Let's say it must be an NP. Okay. So most of the lower bounds that we saw in throughout the course were for explicit functions. However, even before showing lower bounds for explicit functions, uh, we should show that there exist functions which are hard, right? So before showing that there exist hard functions, we must so before showing if our goal is to show there are hard functions in NP, we must first show that there exist hard functions, right? And that is exactly what Shannon's theorem and Riordan-Shannon theorem do. So Shannon's theorem says that most n-varied Boolean functions requires a circuit of size 2 to the n over n. And Riordan-Shannon theorem says that most n-varied Boolean functions require a Boolean formula of size omega 2 to the n over log n. So this is slightly better than lower bound we heard. And like both of these results were proved by a counting argument, right? So basically, what we basically did was the following. We argued that the number of Boolean functions on n variables is much larger than the number of Boolean formulas or Boolean circuits on n variables, right? So if you were to pick a Boolean function at random with very high probability, it won't have a circuit. So let's say the number of circuits is C, the number of Boolean functions is S, then with probability C over S, you a random function will have a circuit. So with probability 1 minus C over S, a random function won't have a circuit. And that's essentially how we prove this. Uh, the so after we proved this, two we saw three explicit lower bounds against Boolean formulas. So we saw Kharchenko's theorem, Nechiporov's theorem, and Subatovskaya's theorem. So Kharchenko's theorem says that if f is an n-varied Boolean function, then for any a subset of f inverse 0 and b subset of f inverse 1, uh, the size of any Boolean formula in these three gates computing f must be at least n a b square over size of f size of b. So f inverse a is just the set of all zeros so that f of x equals 0. And NAB is the size of the set x comma y such that x is in A, y is in B, and the x and y differ at only one place. Okay, so x and y are neighbors. The having distance between them is 1. Then we saw Nachiporov's theorem. This theorem says that let y1 to yk be disjoint subsets of x and Si be the number of distinct subfunctions of y of f on yi, then the size of any Boolean formula any over the basis B2, so any Boolean function on two variables are allowed, is at least 1 over 4 sum over I in 1 to k log 2Si minus 1. So this is only for a very particular basis. This is for any basis. And using these two, we obtained an omega n square lower bound on formula size for parity and majority. Okay, so we use this for parity and this for majority. Moreover, we also saw that omega n square is sort of best in both of these cases. So we saw in the problem solving sessions that Kharchenko's theorem and Nechiporov's theorem cannot give you a lower bound better than omega n square for any function family. Okay, I think this was in second or third week. So after that, we saw Subotovskaya's theorem, and this theorem says that for any function f on 0, comma 1 to the n to 0, comma 1, expectation over a random restriction picked from this set. Uh, this set is a set of all random restrictions that leaves epsilon n variables untouched. Is the expectation over random restriction the size of the formula computing f sigma? So f sigma is f with this random restriction applied is at most epsilon to the 1.5 LF plus 1 over 3. And as an application of Subotovskaya's theorem, we show that the size of any formula computing parity is at least n to the 1.5, and the size of any formula computing Andreev's function is at least n to the 2.5 minus epsilon for any epsilon greater than 0. So, Subotovskaya's theorem gives us strictly better results than Kharchenko's theorem and Nechiporov's theorem because they cannot give us lower bound better than omega n square. So Kharchenko's theorem and Nechiporov's theorem give you the same lower bound for different functions. But Subotov's-Kaya's theorem is strictly stronger result, or gives us a strictly stronger result. After that, we looked at an upper bound from monotone formulas. So a formula or a circuit is said to be monotone if it only contains and or against. So it does not contain not against. Okay. And uh, we saw that there exists a monotone formula of size order n to the 5.3 and depth 5.3 log n for majority. Okay. And we also saw in the problem solving sessions that there is a one-to-one correspondence between monotone formula, monotone circuits, and monotone functions, right? So, Boolean function is monotone if and only if f of x is greater than equals to f of y whenever x is greater than equals to y, and x is greater than equals to y whenever this happens. So, for all I such that yi equals 1, xi should also be 1. So if you compare xi and yi coordinate wise, xi should be good. Every coordinate of xi should be greater than equal to the corresponding coordinate of yi. And we saw that any monotone function has a monotone circuit, and every monotone circuit comes with a monotone function. Okay. Uh, then we saw some more upper bounds for some very basic operations, arithmetic operations like addition, multiplication, and division. In particular, we saw three circuits for addition: the ripple adder, the carry look ahead propagator, and the parallel prefix sum circuit. So the ripple adder gave us a circuit with size n and depth n. Carry look ahead propagator gave us a circuit with size n square, depth order log n. And then parallel prefix sum circuit gave us best of both worlds. So this gives us order n, size, order log n, depth circuit. And notice that this is optimal, right? Because like you need to read everything. You need to read every input, so you need at least order in size. And if you have a circuit of size, a circuit with order and leaves, it must have at least order log and depth. If you are looking at circuits with one and at most two, right? Because a binary tree with log and uh, depth has order and input gates. And we also saw a circuit for iterative addition. So iterative addition is the problem of adding m many n-bit numbers. And since using iterative addition, we can do multiplication, a circuit for iterative addition also gives us a circuit for multiplication. And we saw an NC1 circuit for multiplication as well. So addition and multiplication are both in NC1 and division is in NC2. And then we saw that three problems, division, iterated multiplication, and powering are NC1 equivalent to each other. And what does this mean? This means that if you uh, have oracle gates for division, that is, gates that take two numbers x and y and give you the division of x by y, then using such oracle gates, you can do iterated multiplication and powering using just an NC1 circuit. Okay, so for iterated multiplication and powering, you have this special NC1 circuit, which in addition with and addition to and or not gates can also have oracle gates for division. Okay, and this might seem so a little strange because powering is a special case of iterated multiplication, right? So powering is x to the n and iterated multiplication is x1 to xn, where x1 to xn can be different. So if I take all the xi's to be the same, I get x to the n. So powering is a special case of multiplication, iterated multiplication, but even then, the both of them are NC1 equivalent. So after that, we saw some relationships between low depth circuit classes and uniform circuit classes. So we saw that NC1, log space uniform NC1 is in L and log space and NL is in AC1. So by log space uniform NC1, I mean the following. Function family is in log space uniform NC1 if there exists a family of NC1 circuits that compute that function family, and moreover that that circuit family is log space uniform. What do I mean by a circuit family being log space uniform? I mean the following: there exists a log space Turing machine, such that if I feed in 1 to the n as input, it outputs the description of the circuit Cn. Okay, so there is a log space Turing machine which outputs the discrete, which on input 1 to the n outputs the description of the nth member of the circuit family. Yeah, and we saw that NC1 is a subset of log space uniform is a NC1 is a subset of L, and that NL is a subset of AC1. And this later, the second result we saw by we proved the second result by the following thing that path is NL complete and that path is in AC1. And this was using some matrix multiplication kind of thing. Okay. Then we also saw depth reduction for an NCK circuit. So a circuit of size S and depth D equals log n to the k can be converted to a circuit of size poly S and depth order log n to the k over log n. So this gives us a circuit of slightly smaller depths. And if we can reduce this log n to log n, then we would prove that NCK equals NCK minus 1. But we don't expect this to be true. So people believe that NC and NCK and NCK plus are not different. So after this, we moved on to lower bounds for monotone circuits. And the first lower bound that we saw was because of Rasbarov, Allen, and Bopanna. And what this theorem said was that for any k between 3 and n to the 1 over 4, any monotone circuit computing the clique function must have size n to the omega root k. So if I take k to be n to the 1 over 4, I get that n to the omega root k is n to the 1 over 8, which is 2 to the n to the 1 over 8 log n. So this is some exponential, but a super polynomial, right? So yeah, this theorem gives us a super polynomial lower bound for monotone circuits computing T. And this was proved using a method of approximation. Uh, then we saw a couple of theorems that proved lower bounds for against parity for circuit classes AC0 and AC0Q. Okay, so for any prime numbers P not equals to Q, mod P is not in AC0Q, where mod P is the function which is 1 if and only if the sum over I in 1 to n xi is not equals to 0 mod P and 0 otherwise. Okay, and so even though this is a theorem, in the class we saw only a special case of, we saw a proof of only a special case of this. We saw a proof of mod x1 to xn, not in AC03. And for this, we construct, and one at the heart of this proof was the construction of a polynomial of low degree that approximates the OR function and the end function. And recall that the class AC0Q is a class of all languages. They are recognized by circuits of polynomial size and constant depth with unbounded fanning and or NOT gates as well as mod Q gates. So you can compute the mod Q function for free. Then we saw another lower bound for parity, parity not in AC0. Now observe that AC0 is contained in AC0Q, right? In fact, yeah, so the question is, okay, why is this interesting? Well, this is a strict weaker result than this, but it is interesting because the theorem was different. The technique is different. The technique used to prove this was Hastad's switching lemma, which uses random restrictions. Okay, the switching lemma says the following: that F be a KDNF or a KCNF, and rho be a random restriction that leaves Pn variables untouched for P less than equals to half. Then probability over the choice of rho, so that F restricted to rho is not an SCNF or an FDNF, is at most C times P times K to the S for some constants. So what this is saying is, if you take a KDNF or a KCNF and apply a random restriction to it, then with a decent probability, it is also going to be an SCNF or an SDNF, right? And using this, you can convert. And so let's say you have a circuit of the form and, right? So using this, by applying a random restriction to this, you can convert this to an AND OR circuit. And so the entire circuit becomes an AND OR circuit. So by applying a random restriction, what you've essentially done is reduce the depth by 1. You can do this repeatedly. And if the depth is constant, at the end, you would end up with depth 2 circuit computing your desired function in this case parity. And then you can show that, okay, a depth 2 circuit cannot compute parity unless its size is large. And this is exactly how we proved parity not in AC0. Okay, yeah. So then we saw an interesting connection between communication complexity and circuit complexity. So the communication complexity of a relation R subset of X cross Y cross Z, excuse me. So the communication complexity of a relation R subset of X cross Y cross Z is the number of bits that Alice and Bob, two parties, where Alice has X and Bob has Y, need to send each other on input x in x and y in y to compute z so that x, y, z is in R. And the connection between communication complexity and the circuit complexity is the following. So it was proved by Karchemer and Wigderson, and that they showed that for any function f from 0, comma 1 to the n to 0, comma 1, that the depth of f is c. Depth of f is CRF, where RF is the relation x, y, I, so that x equals to f inverse 0, x is in f inverse 0, y is in f inverse 1, and I is such that x and y are indifferent. Okay. Yeah, so this connects the depth of circuit with, sorry, depth of a formula with the communication complexity of the relation associated with that function. So after this, we saw, okay, so far we have considered two main models of computation, a circuit and a formula. We also saw a third model of computation called branching programs. And so branching program is basically a directed acyclic graph. And from every node of the graph is labeled by a variable. And from every node, you have two outgoing edges. One labeled xi equals 0, one labeled xi equals 1, or labeled 0 and 1 because the node is only labeled. And there is one vertex sink, there is another designated vertex source, and every path goes from source to sink, right? And a string, so there are two strings, T0 and T1. A path from source S to string T0 corresponds, okay, so any path from S to T0 or S to T1 corresponds to a string in a natural way, right? So you look at all the edges on the path, and let's say you have an edge going out of xi labeled 1 on that path, then xi equals 1. So every path is corresponds corresponds to a string, right? And so let's say a path P corresponds to a string. So if P is a path from S to T0 and it corresponds to X, then X is not accepted by the branching program. And if it's a path from S to T1, then TSX is accepted by the branching program. So so a branching program also computes functions, just like circuits and formulas. Yeah, and we saw some connection between branching programs and special types of formulas and circuits. So we saw Barrington's theorem. The first part of the theorem proves that for any f, for any Boolean function f from 0, comma 1 to the n to 0, comma 1, the function is in NC1 if and only if it can be computed by a constant with Pauli n size branching program. In fact, the width is just 5. And Barrington's theorem says that the second part of Barrington's theorem says that mod 3 mod 2 circuits are equivalent to branching programs of width 3. And finally, we saw a natural proof barrier by Alvarov and Rudich. And what this result says is that any proof which is which is natural, so which makes use of a natural property, cannot separate NP and P slash poly. And we saw a formal definition of a natural property. We also saw that some of the proofs that we saw in, or most of the proofs that we saw in throughout the course, like Hasta's proof or so Hasta's proof, I think also this the proof of Raspberry-Smolensky theorem, these are natural proofs. So using similar techniques, we cannot expect to separate NP and P slash poly. So if we want to separate NP and P slash poly, we need some new techniques. And some results which overcome this natural proof barrier are known in the literature. Yeah. So this is what we saw throughout the course. And yeah, so that's all I had for today. If there are no questions, yeah, let's end the meeting. Yeah, I really enjoyed the for this course. Yeah, and if you have any questions, you can still ask in the forum. Okay, thanks.